Okay, so I'm going to present the work on polynomial optimization. So this work is funded by the European grant Back to the Roots at Leuven with Benoît. So in this project, we are trying to go back to the fundamental problems of trying to root system of polynomial equations or trying to find the minimum of a polynomial. But instead of using a way of using Grobner basis and exact computation, we are trying to develop numerical algorithms. And we want them to be numerically stable, because if you just use the algorithm designed for exact arithmetics with floating point, it's not going to be numerically stable. So first, I'm going to say exactly what I mean by polynomial optimization. So what I mean is we have a polynomial P, multivariate. So you have in n dimension, and you want to find the vector x that minimizes this polynomial. And so you can also have constraints. So you can have equality constraints, or you can also have inequality constraint, and this x should satisfy these constraints. So sometimes when you do optimization with polynomial, what you want to do instead is to find a polynomial that satisfies some constraints. For example, in control, sometimes you want to find a Lyapunov function that shows that your system is stable, but this is not what we want here. Here we have, when I say polynomial optimization, I mean that we have a fixed polynomial, and you just want to find the variable that minimize this polynomial. And this polynomial, unfortunately, it's NP hard in general. Of course, if these functions are convex and P is convex, then it is a convex problem. But with arbitrary polynomial, you quickly get non-convexity, and so in general, it's not working. And even in the case where you have no inequality constraints and you have actually no objective, so you're just trying to find a number that satisfies this, then you have a system of polynomial equation, and this is already NP hard. But I mean, we can still try to solve it. And I think what jump user would do when they encounter this kind of problem is that they would use IPOP, right? But IPOP is not going to try to exploit too much the polynomial nature of this. And we are going to try to see in this talk whether we can, by exploiting the algebraic structure of this object, to develop other algorithms that can find the global optimum, because IPOP will only find the local solution. So if we try to look at what the Lagrangian looks like, there are two very different ways to do this. So the first is probably closer to what IPOP would do, is to try to find multipliers for the equality and multiplier for the inequality. If you want the multiplier to be free and not have to be non-negative, we can just try to find multiplier and here use squares to make them non-negative. So we can try to find multipliers such that this condition is satisfied. So this would be the KKT condition. And if you can find x and multipliers here, such that this is 0, this kind of satisfies that x is a local solution. But it doesn't tell you that you have a global solution. So when IPOP is going to solve this problem, and it will find this x and this lambda and this sigma, you only have a local solution. You don't know if it's global. Another approach is to try to, it's not trying to find x anymore. Basically, x is going to be some symbolic variable, but instead you want to find, and lambda and sigma now they are going to be polynomials, not just numbers. And you're trying to find a lower bound gamma at the same time. And what you want is that this expression is, this equality holds for all x. So basically, this is a symbolic expression, a polynomial expression, and this polynomial should be equal to this constant gamma. So if you are able to find polynomials here and here, actually a sum of squares of polynomials such that this hold, then what's happening is that you have a proof that everywhere in the state space, for every x that satisfies that h is 0 and that g is non-negative, P is going to be greater than gamma. So you found that gamma is a lower bound to your problem. And that's a self-contained proof of that. And this is called the this counts for the positive Stallensatz, which is a bit more complicated. So this certificate is called the Putinar certificate. And sometimes by doing this certificate, you don't find that as a lower bound actually the true minimum of the problem. But the positive Stallensatz tell you that there is you can make this certificate a bit more complicated by increasing. Actually, this one will work in some situation, but you don't know what are the degrees you need for the lambda and the sigmas. You just know that they are polynomials. So you already have a hierarchy of increasing degree that you should need to try, and that will improve the lower bound. But there are also cases in which this certificate is not sufficient, and so sometimes you also need to multiply the polynomial on the left by some additional decision variables. But there is this positive Stallensatz that's telling you that at least there exists a degree if you at which basically this bound gamma will be equal to the true minimum of your program. So that can be an approach. Now, if you do the KKT approach, of course, just trying to solve this KKT system may not be sufficient. So, for example, there are some corner cases like this one. If you take this polynomial optimization problem, if you try to solve the KKT system, you arrive at this system when x is equal to 0, and you see that there's actually no solution. And the reason is that at this point here, which is actually the only feasible point, the rank of the Jacobian is only 1, because the normal vector to both these sets are parallel. And so there is actually, if you try to, and here the gradient is going to be a vector like that, so this vector is not a multiple of these things. So, but if you're sure that you're not falling into these traps, then you know that basically the optimal solution would be a solution of the KKT. And so actually, instead of, if you want to use the KKT approach, instead of using IPOP, what you could do is actually try to solve this system of polynomial equations. So if you look at this, basically you have 3 variables here, and you just have here wait, I was missing gradients here and you never told me. Are you paying attention? So if here you put gradients, you have a system of polynomial equations, right? So you need to derive this by all these variables, right? And here you have a system of polynomial equations. And if you solve this system of polynomial equations, you will have as many equations as you have variables. And if you root this, you are going to get normally all your solution if you are not in these cases, right? And to solve a system of polynomial equations numerically, there is an approach that we're developing, which is to, so the classical approach is basically you look at all the equation of your system, and you know that if all these polynomials are 0, you know that if you multiply this polynomial by any other polynomial, it's also going to be 0, and you can even sum them. And so you can generate many polynomials like this. And if you want generators of everything you can generate like that, you can basically multiply your polynomial by just monomials. And this is going to generate all the polynomial you can generate if you consider all the possible monomial. And if you put them, all of these in a matrix, of course, it's an infinite matrix, but if you restrict the maximal degree that you can have in this polynomial, you have a matrix of increasing in size by increasing the degree. And so one approach to solve this system of polynomial equation is to take this matrix and to reduce it with Gaussian elimination, or to do row echelon form. But this approach is called the Buchberger algorithm, but it's not numerically stable. So that's not what you would like to do if you're working with floating point numbers. And so instead of doing this, what you could do is actually do an SVD on this matrix, which is much more numerically stable than Gaussian elimination, and that would be numerically stable. But then what would you do with this? So basically, when you one object that's important with this matrix is its null space. Because it turns out that in the null space of this matrix, if you have the condition that the rank of the null space is the same as the rank of the null space if you remove all the rows corresponding to the monomials of the largest degree, if these two ranks are the same, then actually you can recover the solution of the polynomial system from this null space. And so this gap condition is sufficient to finding all the solutions. Okay, so if you do this approach, generating this matrix, doing SVD, and you have this gap, you actually found all your solution, and you didn't have to do numerically unstable ways, things such as quotient elimination. So it's purely numerical approach. Now, in the sum of squares side, it turns out that what you're doing looks quite different, but you're going to end at the same point. So this time you are trying to generate a certificate like this to show that gamma is a lower bound. So what you do to solve this certificate is that you're trying to solve a sum of square program by trying to find the sum of square polynomial. This can be formulated into semi-definite programming and so on. And then once you find this lower bound gamma, I mean, it's very nice. You can say maybe 3 is a lower bound to your problem. But if you're actually interested in the minimizer, that's not the complete solution, right? So because kind of what you obtained the multiplier, so kind of the dual, but you didn't have actually the primal of your problem. So can you obtain the primal as kind of the dual of this dual? So this you can actually do, but you need to take the duality in the conic form. So if you look at the search for these multipliers as a conic program, and you take the dual of this conic program, you cannot recover what should be your x, but what you have instead of just a vector x is that you have a matrix of moments. So you have a matrix of values for monomials in x. Now, how do you obtain x from this matrix of moments? So there is also a whole theory on that, and it turns out that again, if you take this matrix and you remove all the monomials of the largest degree, if the rank of the resulting matrix is the same as the rank that you had before, you have a condition that says that actually this means that your matrix of the moments can be seen as the moments of an atomic measure, and you can recover the centers of these atoms of this measure, and these are actually your solutions. And so you have a very similar condition about the ranks, and you can actually obtain the solution from these moment matrices. Okay, so that's in these two approaches. At the end, you kind of need to work with this matrix, looking at ranks, and you can kind of extract the solution like that. So here is an example. So if you're trying to minimize the Goldstone sprite function, with just the minimal degree that you can use, you don't need to increase the degree of the hierarchy, you obtain this moment matrix 15 times 15. And so the rows and columns of this matrix should be interpreted as being indexed by these monomials. So this should be thought of being the moment of the monomial you obtain by multiplying 1 with 1. So that's the moment of 1. So it should always be 1, actually. So that's not very interesting. But this one here should be interpreted as 1 multiplied by x2. So this is the moment of x2. This one here, it's 2, 2. So it should be x2 squared. So this is the moment of x2 squared. And so you have all these moments. Now, the rule of the game is that you should try to find some measure such that if you do the moments of this measure according to all these monomials, you should guess always all these values. So can you guess the minimizer of the Goldstone sprite function from this matrix? You can. Now, if you do the flatness condition, all the highest or the monomials are the one of degree 4, so it's the last 5. So if you only take the first 10 by 10 block, if you look at the rank, it's actually rank 3. And if you look at the rank of the largest matrix, it's not so obvious, because if you look at the SV singular values, you have a kind of two echelon, but you can interpret it kind of as a rank 3 matrices, and you can sort of use the previous technique, and it's possible. I mean, it's possible to kind of extract it, even if the numerics are a bit tricky. But actually, there is a much more easy way to see it. Is that I told you that this is the moment of x2, and this is the moment of x1. And so, if you want to cheat, you can say, let's say that I take a trivial measure, and I just look at only these moments, and I get rid of the rest of the matrix, right? So then you can finding a measure so that the moment for x2 is -1 and for x1 is 0. It's easy. It's just 1 direct centered at 0 minus 1. And it turns out that it's the minimizer of the Goldstone-Price function. So actually, sometimes you can use simple heuristics to find very good solution. In this one, you can actually get the optimal solution by doing almost no work. And this was suggested by Monique Laurent in her book. So in a sense, it looks a bit like, if you think about what we've done, like trying to find this certificate using sum of squares. We have this positive standard set that tells us that there is a very large degree for which this is equivalent, but because we are doing it for a lower degree, we're kind of solving a relaxation. And so this moment solution is kind of the solution of a relaxation. So what we know very well in this community as a relaxation is the integrality relaxation when we're trying to solve a mixed integer linear program. And when we're solving this relaxation in a branch and bound and we obtain a fractional solution, what we try to do is we try to round it into a non-fractional solution. And the way we round it, it can be just any heuristics. You don't need to have any proof that this is a good it's just a heuristic. Any way that round this could be good. If you just saw that in practice, it allows you to find feasible solution with good value, it allows the branch and bound to find good upper bound, and that's only what you need, right? So in a sense, in here, if we just have this heuristic that works well in practice, basically we don't need a proof to tell us that we are going to get the optimal solution. We just need good method to find good solution in practice, because we already have this certificate that rigorously proves us that we have a lower bound. So how we find upper bounds, it can be anything. Once by any way, we find a value such that P of x, the value is feasible, and P of x as this value is equal to gamma, we will know that we have found the optimal solution. But the proof that this is optimal is only contained here. The way we actually find the feasible solution, it can be any way. So there've been all the developments of this sufficient condition and things like that, but we don't really need to have any rigorous way to do these things. It can be purely heuristics. And so if we want to make an interface to do this approach, doing this sum of square hierarchy to try to find this lower bound with the certificates and then these upper bounds by trying to round these moment matrices, actually it turns out that the design of JUMP is exactly what we need, because JUMP was designed to be a very good interface for mixed integer linear program, and because we're also kind of solving a relaxation and trying to round it to a feasible solution, we have all the elements we need. So as I explained, if we don't have the flatness property, we can still obtain a heuristic that obtain good solutions. And then we need to report the solution. We have the objective bound attribute in MOI. This is perfectly what we need to return the bound obtained by the sum of squares. And then among all the solutions that we will find like this, we will find some solutions that are feasible, some solutions that are almost feasible, some solutions that are not feasible, and we will be able to report them all to the user, because we can report multiple solutions, and we will be able to say actually, well, this one is actually feasible, this one I report to you, but actually it's infeasible, just I found it. But you can, and in the order of the solution, you can first sort by giving first the feasible, and then the almost feasible, and then the infeasible. And then among all the feasible ones, you can sort them by the one having the lowest objective value, for instance. So actually you don't need a custom interface for polynomial optimization. The jump interface is already exactly what you need. And then for this issue of this hierarchy of increasingly large degree, it's kind of tricky because so we know that for any degree, we just need to solve some definite program. So this is polynomial time, so this is fine, but we don't know which degree we need. And when we increase the degree, the size of the program that we need to solve grows exponentially. So usually for low degree, you will get quickly the solution, but if you increase the degree, it will get more and more difficult. So if you just do a for loop and increase the degree until you find a feasible solution for which the objective value match the objective bound you get with sum of squares, it will usually be a bad approach because the user will at some point see probably a good solution, and then you will see your solver starting to solve a very large SDP, which will either crash because of memory or will be very long, and we just want to control C. And when your solver is killed, then it will not be able to take the solutions anymore. So a better interface is to, when you do optimize, you just solve for 1 degree. Then the user can see what is the bound you obtained, what are the solutions you found, and things like that. And if he wants to be greedy and solve for the next degree, he calls optimize again, and then you solve the next degree of the hierarchy. And so in that sense, the fact that in jump it's not just a one-shot functions, it's like a stateful optimizer for which you can get and set things and call optimize, is very appropriate to do these kind of things. Okay, so then another thing that's very useful is that Oscar have just added nonlinear functions in jump. And so what we can do now, if you want to do polynomial optimization, is so let the user create the problem as a nonlinear function, because it's very easy in jump to specify a nonlinear function. Then if he wants to use IPOpt, he can IPOpt, we just get that. But then if you want to use polynomial optimization solver, we'll first try to bridge this into a polynomial function. So we read the expression of the nonlinear function and we try to see if it's a polynomial. If yes, we convert it into a polynomial structure. Then if he wants to use a QCQP solver, like Alpine or Gurobi, then we basically need to transform this into quadratic function. So when you have a monomial that is larger, you just decompose it by introducing auxiliary variable. Then if instead he wants to do sum of squares, then we can do, we have this optimizer that is going to do this hierarchy and use this inner conic solver under the hood. And if instead the user wants to solve this by solving the KKT system and an algebraic system, then he can use this optimizer in PolyJump that is going to create the KKT system, use an algebraic system solver using the interface in this package, and then return the solution back. So what's nice there is that basically you have just one model, completely solver independent model, and then you can use these 4 kind of solvers that are completely different from exactly the same model. You just need to change this one line in jump that specifies the solvers, and all the rest would be done automatically. Now, one thing that might seem weird here is that this bridge can fail. Like, it's kind of weird to create the model in a nonlinear form, and then after that try to to convert to polynomial, while it might not be a polynomial, right? So this might fail. So is that a good design to create a bridge that is probably going to fail? Well, actually, we're already doing that, and nobody's complaining. So we have this bridge from quadratic function to second order cone, and this is always failing if your quadratic function is not PSD. And we will see few complain about that. And actually, we want to continue to do these things, because what we want to do is, when the user gives a nonlinear function to a conic solver, we want to try to do DCP. But if this nonlinear function is not DCP, it will also fail. So are we completely going on the wrong way? Well, actually, I think this is fine, because in jump, remember that the user, it decides what is the solver we need to use. We have, like, if the user doesn't give any solver, we are not going to take a default choice, right? So in a sense, the problem is completely specified. It just says, here is the model, here is the solver, this is the pair that I want to use. Do the best to try to make them communicate. So in a sense, if you use a conic solver with a nonlinear problem, we can either say error, like it's not possible, or try to use one of these bridges that may fail. So because this is basically the only possibility we have, I think it's fine that they may fail. Okay, so the last point I want to make is that, so I've presented these two approaches, or trying to solve the KKT system with the Macaulay matrix, or trying to do this sum of square approach. But actually, I show you that at the end, they need to do something quite similar. But I think that in addition to having a similar end, they can kind of work together. Like they both suffer, for a fixed degree, they are like polynomial and they use nice algorithms that are numerically stable, but they both suffer from this idea that if you increase the degree d, they are both going to be exponential. So for both of them, you can easily solve the first degrees, and then you just don't want to increase the degree. And you want to know if it's possible to, while staying at low degree, do a bit more work, but not go to the next level. It seems that when you don't obtain your solution, what you obtain in both cases are kind of complementary objects. Like in the sum of square case, basically, you're trying to find these measures that prove that your polynomial is a bound. So you have a measure where the support is kind of pushed toward all the points where the polynomial is very small. And instead, in the Macaulay case, you're trying to find critical points. And the critical points, they can be anywhere where the polynomial, it can either be local maximizer, and it can even be complex solution of the algebraic systems. So somehow you usually have a small set of solutions because they are communicated critical points, but they are not at all going to be where the polynomial is small. And so in a sense, what you really want is something that's at the intersection of the two. And what's nice is that somehow this moment matrix, when it doesn't give you a point, it's actually kind of giving you a system which may be like not a system containing just the solution, but it could be like a one-dimensional variety, for instance, that may actually contain the solution, but also other things. And if you intersect with the KKT, because the KKT contains only the critical point, you may actually single out the solution you want. But one thing that's very tricky is that this system is actually very noisy. But because this approach for solving the algebraic system is actually very numerically robust, because it's based on linear algebra, when you can really control the numerical robustness and what's happening, this is actually a feasible approach. And so if you want to, so I'm going to end with this slide. So they're actually, in the implementation, they're actually already kind of sharing a lot of different steps in these different packages. And I think if you want to make this method work and to be also practically useful like IPOpt, you need to find kind of a way to make these two interact. And instead of just doing this one step and going to the solution, and if it fails, you just increase the degree, try to continue in this space and try to go to some kind of loops. And try to stay at the same degree, but try to do a bit more work by working together. But I leave the detail for later.